Hello, it's Keith here, and this is lesson 10 of the Photon series of Z80 programming tutorials, in which we are working on my little Tron game and we're porting it to lots of different systems, and here it is on the Sega GameGear. Now, we looked at the Master System last time and we used the MSX1 compatibility mode, where we were effectively splitting the screen into three tile areas of 256 tiles, which allowed every pixel of the screen to be different, but it gave us a rather limited color palette. This time we're going to be looking at using the 16 color mode and using the almost 512 tiles to do the same thing. So that's the GameGear version, and this is the Master System version here. Slightly bigger screen on the Master System, but still not quite full screen, so we're not perfect, but we're doing okay. Anyway, we're going to look at the code that does this today, and we're going to learn how it works. Let's go over and have a look. Now, the Master System can use up to 512 tiles, but that would actually use the full 16 kilobytes of video RAM, and part of that video RAM, the top part, is used by the tile map itself, so we can't use all of those tiles. So we have a practical limit of 448 tiles. Now, on the Sega GameGear, we're going to define a 20 by 18 screen, because that's the entire visible area of the screen, and that's going to use a total of 360 tiles, so that's absolutely no problem. On the Sega Master System, though, we are really limited by the number of tiles. The screen I'm going to define is 24 by 18, so a little bit wider, and that is a total of 432 tiles out of a possible 448, so that's left us with 16 tiles, and one of those tiles is being set to black to fill the unused area, because otherwise it would go completely crazy. So that's why we're selecting that particular size. It's all to do with the limitations. Now, this time we're using our normal VDP initialization. We're using the regular Sega Master System or GameGear screen mode, nothing unusual this time. And what we're doing here is we are defining the palette, and then we're defining the tile map, and we're filling the central area of the screen with consecutive tiles, so that we can then set those later within the Pset routine. Just like before, where we were using a 768 area, we're using a smaller area, but we're still going to calculate the position within the pixels and set one of the pixels of one of the tiles according to the pixel position we want to draw. So here we're setting consecutive tiles for the screen area, and then here is going to be the start of our code. So here we are defining the size of the screen, and here we're defining the four colors the game's going to use. And we're going to use 1, 2, 3, and 4. On a 16 color system, that's very obvious, but on a 3 color system, color 4 would have to share color 1. Now, the user RAM is the game data variables, so we're just clearing those there, and we're showing the main menu. And then we've got the loop for the game code here. So this is it here. We're going to go over it again. If you saw the last time, you all know this, but we'll cover it just one more time. Now, the game has the potential for a boost mode, and this is where the player moves super fast. If I just start the game here, if I remember my controls, if I hold down fire, I will move faster, and you can see that there. The other thing to notice is if I press the left key and hold it, I only move once. I have to actually release the key and press again to turn around, and that's so we don't just immediately collide into things, because if it kept turning too fast, we'd just end up colliding with ourselves. So those are the things we're going to see in here. So the first thing we're doing here is we're checking the boost. Now, the boost will move as every tick, and boost off will move every other tick. Unfortunately, I'm drawing the boost counter in the corner because my vector font's a bit slow, and that takes some time, so we have to alter the speed of the game depending on if boost is on or off. What we're doing next is we're going to check the key reading. We're going to read in from the joystick and see if anything's pressed. If nothing's pressed, we're going to clear the key timeout. That's so the key's been released. If a key is constantly held down, we're going to ignore the key presses. But in this loop, we're just updating D with any key presses that have occurred for processing later. When we get down to here, we check if the key timeout has not been cleared, and if it's not, we're going to skip all the way over here and we're just going to update the game. Otherwise, we're going to process the keys. So we're turning off boost here, and then we're checking the directions. We set HL to the player direction and IX to the acceleration of the player, and then we check if left or right are pressed, and we change the player direction accordingly. Set player direction will update the rotation of the player, and it will set the acceleration of the player according to the direction. That's what's happening there. In both cases, we're setting the key timeout so that, again, they have to release the direction before turning again. If the fire is pressed, we check if there's any boost power left, and if there is, we set boost to 0, which enables boost. The actual decrementing of the boost power, updating the counter and all that kind of thing is done by handle player, and the CPU AI is done by handling CPU, and also the collision detection, of course, is going on there as well. Now, we're not going to cover the joystick reading and the fire buttons and things. This is all the same as in YQuest, so if you don't know how to do that, take a look at YQuest or even the Simple series. I did a joystick example in the Simple series. It's all identical, so I'm not covering it again. Now, what we really want to focus on, though, is the Pset routine and the point routine, because these, I think, are the interesting thing here, because we're effectively treating our tile patterns as a simulated bitmap screen, which I think is a bit curious. So what we're going to have to do is we're going to have to read in the 4-bit planes that define an 8-pixel wide strip within the pattern data that makes up the screen. We're then going to have to remove one of those bits from all 4-bit planes that is the pixel we want to change, and we're going to have to OR in new bits depending on the color we want to set. That's exactly what we're doing here. So first of all, we need to bear in mind, of course, that because we're working in bit planes, each byte contains data for 8 pixels here. So we've got this mask here, which will select the corresponding bit depending on our pixel. Now, this routine will run with BC set to the XY position and D set to color. So the bottom 3 bits of B is the bottom 3 bits of the X position, and that's the position within the byte of the pixel we want to change. So we're just getting a mask from pixel mask. We're storing the mask for the pixel we want to change in D, and the pixels we want to keep in E, the current screen pixels, and we're going to push those later into DE and pop them out as BC down here. We're then using calc VRAM address, which is going to calculate the video RAM address of the pixel for the position we want to change within the tile pattern, that is. And we'll have a look at that right now. Here it is. So we need to calculate the position of the bitmap within the pattern for the address of the screen we want to change. So there's 8 pixels per byte, so the bottom 3 bits of the X position, we're just stripping that there, and then we are multiplying this effectively by 8 because there's 8 lines per tile, and then by 4 because there's 4-bit planes per line, and that will be the correct X position for the tile we want to change. So we're doing that just here. We're then taking the Y line within the tile, that's the bottom 3 bits, and we're multiplying that effectively by 4 because there's 4-bit planes per line. We're then taking the remaining bits of the Y position and we're multiplying those by the width of the tile map. Now that is going to be effectively 20 for the layout of the GameGear, or 24 for the layout of the Master System. And because multiplication is a bit of a pain, what we're doing is we're doing bit shifts, and we're effectively going to multiply by 16, and we're going to add that to our calculated position, and then we're either going to add 8 to effectively multiply by 24, or by 4 to effectively multiply by 20 here. And so we're doing that there, and we're adding that in just here. Now the base of the pattern data is memory address 0, so we're not having to add anything else there. But once we've done all of this pain, effectively we have calculated in HL the VRAM address of the line of the tile that we need to change for our XY position, assuming we've not changed the screen, because of course if you change the screen size here, those calculations would not work, so you need to create new calculations. But of course there's no reason you can't do that if you wish. So we've calculated our memory address here, and then we're setting to reading, and we did that last time. We'll just look at it again. We just write the HL address to the control port here, and that will select it as a read address so that we can read in data from our VDP port just here. So we're reading in the 4 consecutive bit planes. We're masking with C, which is the bits of the screen that we want to keep, and we're storing those in IXH, IXL, IYH and IYL. So we're reading in all 4 bit planes into our extra registers here, and we're going to then write them with the new data down here. So we've done all of our reading. We now set the same address to a write address, and we're now going to do some writing. Of course, if we did this alternating between the two, it would take a lot more time, so I think this is the best way of doing things. And now what we're going to do is we're going to look at our color in D, and we're going to pop bits out of it, and if the bits are 1, we're going to need to OR in the mask for the pixel that we read in from our lookup table here, and of course that is this thing here. So we're going to set the corresponding bits for the pixel depending on the color, and we're setting each of the 4-bit planes just here, and we're just writing them back to the screen memory. Of course, if we just want to clear the pixel to 0, we would just write back the data without setting those bits, and that would do it. So whatever the color we want, that is setting it with that. Now the point routine is kind of similar. We're doing all the same stuff here. We're getting the read address, but this time of course we're not doing anything like this. We're not caching the data here and then writing it back here. What we're doing instead is we are reading in a bit from the bit plane. We're setting a bit of the C register here, which we're starting as 0. We're setting bit 3 and we're shifting to the right 4 times. Now effectively the first one we set will be shifted all the way to bit 0 by the end of this, and by the time we've finished we've set the bottom 4 bits of C, and that will be the effective color number of the pixel we wanted to look at, and that's how we are testing the pixels. Now of course the game I'm doing here doesn't really care what a color is, it just cares if it's black or not, but I thought for completeness we wanted to actually try and get the colors back, and that's what we're doing just here, and that's how we're doing it. Now the only things left in this is the fill area with tiles routine. We did actually look at this. Basically this is the same as the simple bitmap series. We are just calculating the VRAM address of the tile map. The tile map base is at 3800, and that's why we can't use all 512 tiles, because they would actually overlap that. But we're just consecutively setting tiles according to the tile format here. We're just setting them all to consecutive numbers, so from 0 to 512 or 400 and whatever it was. So we're just filling it all in there. And then all we've got left then is this clear tile map routine here, which will clear the entire tile map to 447, and we're doing that to clear the Master System version. We don't need that for the GameGear, but if we don't do that, if I clear to tile 0 instead, you will see all kinds of crazy stuff goes on, because we've now we're using the top left corner of the screen for our unused tiles. So 447 is an unused tile after our defined screen area, and that's what we're using there. The clear screen routine is just zeroing all the pattern data for the tiles that make up our virtual screen there. And there you go. So that's basically the entire game. As I say always, you can go to my website and download the source code to this. You can have some fun with it, hopefully, and if it's useful to you, go ahead. Maybe there's a way of making the pixel plotting routines a bit more efficient. This was the best I could come up with, but it certainly seems okay. And I had a lot of fun making these tile-based systems plot pixels, because I'm much more used to bitmap screens, so I thought it was a bit of fun. Anyway, if you enjoyed it, please like the video and subscribe, because that always helps me out. And of course, go to the website and download the code. Thanks for watching. If you've liked what you've seen today, please consider backing me on Patreon. Every video I make takes about 5 to 10 hours of development, research and documentation for the website, so it really takes a lot of time, and it's only through the continued backing of my patrons I'm able to keep justifying putting the time in, to be honest. So if you are interested, you can support me on there. I release my videos to the Patreon backers way before regular YouTube viewers, and also when questions come, I always prioritize the Patreon backers when it comes to requests and suggestions and things. Although of course all my videos do come out to non-Patreon backers eventually, because I do consider them to be an educational content that really everyone should have access to. But as I say, if you want to support me, you can do so on Patreon. Links in the description below. Also, I now have a Teespring store, so if you want to buy some Chibi Akumas or learn ASM merchandise, you can go ahead and find something on there, and I'll probably be releasing some new designs if people seem interested in it. Anyway, whatever you do, thanks for watching today, and goodbye.